it's a pleasure to be here and today. So I will first start by telling you roughly the status of very light dark matter direct detection experiments. The short summary is that within the next couple of decades, we hope to be able to probe most of the interesting parameter space. But first, I will start by motivating a bit why this particular kind of dark matter is interesting. And then towards the end of the talk, I will first very briefly tell you why looking for very light dark matter and looking for gravitational waves have a lot of common features, to the point that you can most of the time just take an experiment that looks for one and use it to look for the other. But then I will also tell you why it's so much, well, as you probably know or imagine, it's much harder to look for gravitational waves, to the point that we will almost prove a theorem that it's not going to be possible within probably our lifetime to detect anything much above, let's say, 10 or 100 kilohertz. So the talk kind of naturally splits into two parts that don't talk to each other too much, but I hope that this will give every one of you something to be interested, to be excited about. So let's start with dark matter. As you know, we have evidence for its existence from gigaparsec. So up there is a picture of the CMB by Planck, all the way down to kiloparsec, and also the scales in between. This here is a picture of our galaxy by Gaia, so not a very new one at this point. The problem is that, we've seen it gravitationally, and we know some of its properties, but at the microscopic level, so the one that a particle physicist like me cares about, we know very little about dark matter. So this line represents how much the dark matter mass can vary and still be consistent with experiment. And this is to scale, and like roughly 3 pixels are 1 order of magnitude. So here there are 80 orders of magnitude. It goes from about 20 orders of magnitude lighter than the lightest particle we know exists, the neutrino, all the way up to a small planet. And that's not even the end of the story. So if you start asking what the coupling to us can be, or the coupling to itself can be, there are another about 50 orders of magnitude in coupling to the standard model, and another 50 orders of magnitude in coupling to itself that are fine. I'm not saying that every single point in this three-dimensional space is allowed, but an order of one fraction is. And additionally, this axis here with the coupling to us, it's actually a multi-dimensional axis. So I'm collapsing into it about 20 different possible couplings to the different particles in the standard model. So somehow in the particle physics community these days, many people like to just go into this parameter space and look for whatever they can look for. However, I mean, it's almost guaranteed that if you do that, you're not going to find anything before you retire and before the children of your children retire, if you just like try to explore randomly this parameter space. So I prefer to try to find regions that are more motivated theoretically and start focusing our efforts there. And at the moment, I believe there are two regions, at least in mass, which then are also correlated to the coupling, as I will show you, that are more motivated theoretically. One is close to the mass of the heaviest particles we know, so the Higgs bosons and the other electroweak bosons. And the other one is that spans a few orders of magnitude in the lightest range that's experimentally viable. Let me start by telling you a little bit about this range around the Higgs boson, which has been the most sought after for the past few decades. So first, just a remark, which is that I'm going to use natural units. So I'm going to set H slash and C to 1 and measure everything in EV. So in case you find some formulas that have funny units, it's because of this. All right, but let's get to it. So these dark matter particles that have masses close to the Higgs mass have been looked for decades with a huge effort, and the reason is that they're very appealing theoretically. For example, if you just take any particle with no electromagnetic charge and you couple it to the weak interactions in the standard model, for example, the Z boson, it turns out that it has the right abundance almost automatically. You just have to imagine that the universe was reheated at a temperature larger than its mass or comparable to its mass. And then you let the standard cosmological model and the standard particle physics model run as they are, and it works. So this particle can be dark matter. Additionally, well, there is a puzzle related to the Higgs mass, which is that if you just take the theory of nature as is, you expect it to be close to M Planck, which is about 20 orders of magnitude larger than what it should be. However, if you modify slightly the theory of nature we know and add a new symmetry not too far from the Higgs mass, everything makes more sense. And these particles that couple to the Z boson have no electromagnetic charge and the right properties to be dark matter are predicted into these theories. So for example, in supersymmetry. And so these kind of dark matter candidates have been, well, very popular in the past decades for these reasons. So they're a small extension of the standard model. They have a simple and predictive cosmology and potentially are related to another problem in particle physics and its solution. These are still very interesting dark matter candidates, but as I said, vast experimental effort has been directed at them. And if you just ask what's the prediction in this plot with the mass of the particle and its interaction with us for experiments that exist, if you write down the simple model I did in the previous slides where these particles couple to the Z boson, it's somewhere around here. So about, I don't know, 10 or 20 orders of magnitude above what's currently being probed. Many simple and motivated models are still alive, live around here. And with a combination of these direct detection experiments and other ones, we're going to probably be able to probe in the next 10 years or so. So I would say that it's still totally fair to think that this is the most motivated dark matter candidate out there. But, well, I think that there is another one that is at least as motivated as the one that I just described. And so let me give you a few details about what I'm calling ultralight dark matter. Yes.
So what do you do to move you know, something that has a coupling to the Z boson down
Yeah.
to the bottom of that graph to hide it? Because you don't have that much freedom with the coupling.
No, indeed. So well, let's say the simplest thing you can do, which is, I think, borderline, like it's close to the boundary here, but still in the white, would be, so let's say take a triplet of SU2, so a particle that looks like this. Let's even just take this, that's it. Okay, then the neutral one is naturally a little bit lighter than the other two because the other two couple to the photon and get a correction to their mass from the photon. So already, if you do nothing, let's say the neutral one is the lightest. And then if it's really a triplet, just because of its quantum numbers, it doesn't couple directly to the Z. So this vertex is just not there. And so the way you see a signal in those experiments is that the neutral one comes in, it emits a W, and it turns to the charged one. And then it emits another W and goes back to itself. And then, okay, here you have some standard model particles, say in the nuclei there. And so, well, you're trading. So here there is a small coupling. Here there is another small coupling when you scatter this particle with us. And so you're essentially trading two small couplings for 4. And here there is also a loop factor. So that's one way. Okay. Then, well, there are other let's say, more detailed ways. For example, if you have a doublet, so what people call an Xeno, there is some accidental cancellation between the Z, the X, and the W scattering, so that brings it down in certain nuclei. But let's say this is maybe the cleanest reason why something like this could be still alive. And okay, then there are other models, but it's more detailed, let's say. No problem. Okay, so let's look at this light regime instead and see what dark matter here looks like. So the first fact about ultralight dark matter that I wanted to highlight is that it must be a boson, and for kind of a nice reason. So this is one of the rare cases where quantum mechanics gives you a macroscopic effect that you can compare with a classical effect. So if you look at, say, dwarf galaxies, these are predicted to have a large spatial density of dark matter. And then if you imagine that dark matter is a fermion, well, you cannot have more than one in the same phase space shell from Pauli exclusion principle. And so you can just calculate what's the minimal velocity, so the Fermi velocity of this, say, gas of fermions in the galaxy, given a certain spatial density. And for the galaxy to exist, you need this velocity to be smaller than the escape velocity that you compute from classical gravity. If the inequality is reversed, then these dark matter particles have enough kinetic energy to just fly away from the galaxy. And since this density here, so you can see that this velocity is growing pretty fast with the mass. And so as you go to lower and lower masses, you get a bigger and bigger velocity. So at some point, if you try to make dark matter too light and be a fermion, you predict that some galaxies that we observe don't exist. And so this essentially is telling you that everything that's dark matter below here, so a kilo-electron-volt in my units, must be a boson. The second fact that's going to be useful for us is that, again, if you use the dark matter energy density, for example, measured from the CMB or local observations, and you ask, what does it mean in terms of how many dark matter particles you have in a de Broglie volume? You find that when the mass becomes much smaller than an electron volt, this number becomes large. And so this is just one of the many ways in which you can take the classical limit of quantum mechanics. So essentially, these particles, if we think about masses much smaller than an electron volt, as we're going to do today, they behave like classical fields. So we can describe them as classical fields. So that's roughly our target, let's say. And so let's see if it has the same qualities that I described for the other kind of dark matter. So we would like it to have a simple and predictive cosmology. So we want a simple way to have the dark matter abundance that we observe today. Ideally, we would like it to explain something else in particle physics if it wants to compete with these other particles I described. And finally, well, okay, if you like minimality, it can also be a minimal extension of what we know to exist. Here, I'm just going to imagine to adding to the theory one scalar field, so 1 degree of freedom. So we just said that we can describe it as a classical field, and so it's going to be a classical field with some potential. And the curvature of this potential just gives us the mass. And as I said, we're going to take masses smaller than an electron volt. And as you know, well, throughout the history of the universe, we have we know that the universe existed at energies much, much bigger than an electron volt. So as far as the energy scales in the problem involved that exist in the problem are involved, this curvature here is practically non-existent. This potential is very flat. So there is no reason why this classical field lives its own life at the minimum. In general, we expect that it received some kick and gained some potential energy, just because the energy scales in the evolution of the universe were much bigger than the ones typical for this potential. So you just expect this in general, essentially from dimensional analysis, not much more than that. And then you can ask, how is this potential energy going to evolve? And as we said, this is a classical field, so we can write a classical equation of motion in the Friedman-Robertson-Walker background that gives us this factor here. And this equation, well, has two regimes. So initially, the universe is small and dense and hot, and so this Hubble parameter is big, and the friction term dominates. Then the field is stuck wherever it was displaced. But as time goes by, the universe expands and cools down, and Hubble becomes smaller and smaller, until at some point it becomes smaller than the mass. And when this happens, okay, you just solve this equation up there, which is just a forced harmonic oscillator. Which is just a damped harmonic oscillator. And you're going to get some oscillations that are damped. And interestingly, the amplitude of the field redshifts exactly as you need it to redshift to get cold dark matter. So the energy density in this field is given by the amplitude squared times the mass squared. And so you get something that redshifts like z cube, so like cold dark matter. And essentially, if you want to explain the amount of dark matter that we see today, this amounts to fixing the initial condition. So how much it was displaced from the minimum at the beginning. And so you see, I just added to the theory one scalar, and I essentially done nothing to it. I just described it based on what we know on dark matter, and found that it can easily reproduce how much dark matter we see today. I'm still not checking the last box, but now I'm going to give you an example of a very light dark matter particle that can check also the last box. And this particle is the axion, which is related to a problem in particle physics that we call the strong CP problem. Very schematically, one can describe the problem in the following way. So there is an operator in the standard model Lagrangian, which is made up of two gluons, and does some coupling in front that I'm going to call theta. If theta is 0, the neutron looks like this. These are two down quarks, and this is an up quark. So classically, okay? So the neutron looks like this classically. Let's forget about all the gluons, the quantum fluctuations, but the classical picture is enough to understand the problem. So when theta is 0, the neutron looks like this. This quark has twice the charge of these two. So you see there is no electric dipole moment. So this object is neutral and has no electric dipole moment. Instead, if theta is different from 0, the neutron looks like this. So the quarks make a triangle with some angle here at the apex, which is proportional to theta. And so you see that there is an electric dipole moment. This guy has a positive charge, and these two have a negative charge. And now you can go and try to measure this electric dipole moment, which has been measured very precisely to the point that a bound of order 10 to the minus 10 has been set on this parameter. The problem is, again, based on symmetry and what we know about the theory of fundamental interactions, we expect this parameter to be order 1. So now we have to explain why we find it to be 10 to the minus 10. And it turns out that there is a very simple explanation that involves a particle which is just the same as what I described for dark matter so far. So this particle is known as the axion. And essentially, you imagine that you introduce a new global symmetry at the scale Fa. This global symmetry is spontaneously broken, and a Goldstone boson comes out. So essentially, you expect a massless particle in the spectrum as a consequence of the nonlinearly realized symmetry. This particle, again, just purely based on symmetry considerations, is going to have derivative couplings to everyone in the standard model. This one is also derivative coupling, but it's a special one that can generate a potential for this particle. And it's the only one in the standard model that can generate a potential. So if you just let the theory do what it wants to do based on symmetry, you're going to have a potential for this particle coming only from this operator. And it turns out that this potential exactly cancels this effect in the neutron electric dipole moment. So, okay, so we've now checked also the last box. So you can have a particle that is dark matter in a simple way, can also solve another problem in particle physics. In principle, there are also more sophisticated ways also to relate this particle to the puzzle of the Higgs mass that I mentioned at the beginning, but I'm not going to talk about it. For now, well, I'm going to be happy with just these 3 reasons for thinking about this kind of dark matter. And if you really want the axion, so this particle that couples to two gluons, to be dark matter, then you can also make some prediction. So this coupling to two gluons below the QCD scale, so when the strong interactions actually become strong, give you a mixing between the pion and this particle. And this mixing essentially allows you to fix its properties. So it gives you a mass once you fix the scale FA that determines the coupling to us. And also it gives you a series of couplings to the standard model, the most interesting of which for today will be this coupling to an electric and a magnetic field. If we want to look at this particle, let's say a bit more quantitatively, here I'm showing you the mass in electron volts versus its coupling to two photons. On this orange line here, this particle is solving the strong CP problem I've been talking about. So this orange line is kind of the prime target for the searches for this particle. On this purple line, essentially we have a particle similar to what I described, but that does not necessarily couple to gluons. And on this line, you have some sort of natural prediction for dark matter. So I can tell you more if you're interested, but these two lines are really just to guide the eye. So I would say that are two of the most motivated regions of parameter space, but in reality, if you make the models a little bit more complicated, you can populate any place you want in this plane.
But also the CP relation or not?
These ones on the purple line, they don't. So essentially, if you want to solve the problem and you don't want to any tuning, you're going to be either on the orange line or below. But so if you want to solve the problem, you will always have at least one particle on the orange line. Then you can have more that mix with it, and then they live down here. For that particle that solves the problem, there is also some sort of natural spot where it can be dark matter, which is here. So if you want these purple points here are the ones that in the simplest model give you everything, give you dark matter and the solution to the problem.
Well, this means that the parameter space that's proposed is extremely small unless you don't rely.
Well, in the simplest model, where you just add only that particle and nothing else with that coupling. But if you, let's say, already add one more degree of freedom, then anything goes, more or less. Yes.
What's next? The axion mass in the QCD, I mean, before you integrate out gluons and stuff?
Before?
Yeah.
No, before, so at energy is much bigger than the QCD scale, it's massless. So. Yes, it's true that, but they're not that big. So if you let me.
I thought that it's very hard to have it much lighter than some scale.
So indeed, so that's what I meant when I said that if you want to live up here, you need to tune, because so this coupling to QCD is always going to give you some sort of irreducible contribution to the mass, which is of order m pi squared f pi squared over fa squared is ma squared, which in the standard model it's like 80 MeV to the fourth over this FA. And this coupling here is proportional to 1 over FA. So when you fix the coupling, QCD is always going to give you a contribution to the mass at least as large as the one on this orange line. If you want to go above, you have to somehow to cancel this mass. And so that's what I meant by tuning, let's say. So I don't know if that was your question, but instead, if you want to go below, it means that the axion given a coupling, it's heavier than this. That's much easier to do because you can just add another particle to the theory which is heavier and mix a little bit with it. So yeah, I guess the bottom line is that it's easy to go here, it's hard to go here, and of course experimental it's the opposite. It's much easier to go.
So, but this is naturally okay. It's naturally okay to have it so light. No.
Yes. No, sorry. To have it so light. You mean yes. So when you're on the line, that's the natural QCD prediction. Yes. So Yes, so let's say instantons. Yeah, it's an instanton-like effect, but like as you know, instantons like stop to being the dominant saddle of the path integral. At least you cannot prove that they're the dominant saddle of the path integral when the coupling becomes strong. Yeah. So then the way I compute this is with the chiral Lagrangian. But okay. So now I want to get to something a bit more technical and new, which is, okay, how do we detect this particle? Well, some of it will be already familiar to you, but there are also some experiments that are a bit more recent. So to detect it, we have to know how it appears in the laboratory. And well, so if we want we want this particle to be a viable dark matter candidate at these small masses, it needs to be produced cold, so essentially at rest. The mechanism I described, where it's misaligned from the minimum, automatically produces it at rest. But even if you produce it in some other way, you have to find a way to do it. Otherwise, it's excluded by some other experimental constraints. When then galaxies form. This particle falls into the potential well of the galaxy and it virializes. So it gets a small velocity, which is of order, so the kinetic, so this velocity is of order 10 to the minus 3, the speed of light, roughly. And then the last point that we need to keep in mind is that, as I said before, we're going to have a lot of these particles in any reasonable volume. So before I looked at the de Broglie volume, if you look inside an experiment, you're going to get even more. So these are very well described by classical fields. And so roughly what an experimentalist, well, sorry, actually, maybe let me first say another thing. So there are these three characteristics of the dark matter particle for an experimentalist that wants to look for it. And one more thing to keep in mind is that, well, we are here in our laboratory, and there is some streams of dark matter crossing our experiment, but each one of these streams came from different initial conditions, traveled through different trajectories during the history of the universe. And so a simple toy model that describes what we're seeing is that we see a sum of plane waves. If we describe this particle as a classical field, each one with a different phase and also with a different velocity, drawn from this velocity distribution coming from the horizon inside the galaxy. So if you sum all these cosines, you're going to find, just using usual trigonometric formulas, that you have a piece that oscillates fast at the mass of the particle, multiplied by pieces that oscillate slowly. So by slowly, I mean 10 to the 6 times more slowly than the mass, due to this small velocity dispersion. So these objects essentially looks very monochromatic, okay? So if your experiment is looking at less than 10 to the 6 oscillations, this dark matter looks like a delta function in frequency space, or like a perfect cosine. Summarizing its properties, let's say what an experiment would see is some sort of monochromatic classical field with an amplitude that depends on the dark matter energy density, so that we can compute that we have measured, a frequency that depends on the mass, a coherence time, so the moment where you start seeing this slower oscillation, which is roughly 10 to the 6 times longer than its typical period of oscillation, and also, let's say, a spatial coherence, which is about 10 to the 3 times bigger than the inverse of the mass. Okay, so if you want an experiment that matches the frequency of the oscillation of this object, it's gonna see this particle as a perfectly monochromatic classical field until it gets to 10 to the 6 oscillations. And well, this is very nice because we can exploit these coherence properties to resonate with this field. And this is why I'm going to focus mostly on this coupling to 2 photons, okay? Because we've seen that this particle is a nice, coherent, and essentially monochromatic classical field. And the fields in the laboratory that have these properties and we know how to manipulate with large amplitudes are electromagnetic fields. And I'm going to show you in a second more concretely why we want to do it. But for the moment, let's see what happens if you add this particle to the theory. Then, well, the leading modification to Maxwell equations is this one. So you get some extra term for the curl of B. And this extra term essentially looks like an effective current, which oscillates at the mass of the dark matter. If you ask in practice how big this effective current is, well, it's tiny. So let's say you turn on some electric field or magnetic field in your laboratory, and dark matter arrives. Well, then it will interact and give you some other photons, but it gives you 10 to the minus 21 fewer photons than you put in. Okay, so it's almost as hard as looking for a gravitational wave. The reason why it's not really as hard, it's because, well, you know almost exactly the waveform, and the signal is always there. So you have this like cosine that oscillates at the frequency that depends on the mass, that stays always there. It's not a transient signal, so you can just wait and build up on this signal. So when I say 10 to the minus 21, I really mean on this orange line where you also solve the other problem. So the nice feature of this line, other than being motivated theoretically, is also that it gives you a measure of experimental difficulty, let's say. So all lines parallel to this one have a certain experimental difficulty. If you go above and stay parallel, it's easier than staying on this line. If you go below and stay parallel, it's harder. So this, let's say, effective coupling becomes smaller. Okay, so, well, if you ever try to measure anything, you know that 10 to the minus 21 is not something that humanity can do, like out of brute force. My very rough rule of thumb, although this, when I say it, people always like to argue about it, is that we can measure things roughly at a part in a billion without cheating. So just like our most precise rulers or, I don't know, electromagnetic detectors measure things in a part in 10 to the 9. And so, okay, you have to find some clever way of enhancing your signal. And the simplest way is to just resonate. So in my fancy particle theorist language, you set boundary conditions to the photon that break translational invariance. And as a consequence, the photon gets a mass which is proportional to 1 over the size of your boundary conditions. In more human physical parlance, you build a cavity and the electromagnetic fields are some more normal modes in the cavity. And well, if you immerse this cavity into an electromagnetic field and make it of the right size, that is 1 over the mass of the dark matter, then you can resonantly enhance this signal. So this signal is going to build up for 10 to the 6 oscillations of the dark matter field. And this idea, well, it's an old idea, and the most successful axion dark matter experiments are based on it. So all these gray areas that you see in the plot that touch this orange line or almost touch this orange line are just this. So a big, like a cavity, in this case of, let's say, order this size, immersed in a big magnetic field, and it gets you there. So, okay, that's a nice experimental concept, which has been well tested. The most famous experiment here is ADMX, but there are many others that are just as nice. And in the future, they will cover, let's say, all this region on this line, including the most promising point in the simplest model. However, well, there is no way that this idea can probe anything much below or much above. Well, the reason why it works so well is that these cavities in that range are roughly human size, okay? They're like tens of centimeters. So they're objects that we know how to manipulate well. So we can build them with very large quality factors, meaning that they look a lot like a perfect harmonic oscillator. And also, they're coupled to electronics that we know how to build with very low noise. Practically, we know how to get to the standard quantum limit of the electronics at those frequencies. However, as you go this way, the frequencies become lower and lower, and so you need to build bigger and bigger cavities. And at some point, the idea just doesn't work anymore because you cannot control them as well. Also, the electronics becomes worse. So one option that was proposed, well, now about 8 years ago, is to, instead of using a cavity, to use another type of resonator, so just an LC circuit. And here the frequency at which it resonates is decoupled from the size. It depends on the inductance and the capacitance. It's still hard, well, you still need to make it big because the probability for this dark matter particle to interact with us depends on the volume, so it's still hard to do. But okay, they project that they're gonna be able to extend by a lot the reach of current experiments with this trick. Of course, okay, when you look at these lines, and I include my lines that I'm going to show you in a few slides, you should always be skeptical. So when these lines are typically theorists drawing them in their theory papers. They always hide some non-negligible amount of experimental effort. So to give you an example, this one here that can cover this huge range in, so maybe it's not, well, this range is huge, so this is a log-log plot. So it's really making a huge dent here. So this one requires building a magnet as big as CMS, so probably the biggest magnet that there is now on Earth, turning it on roughly with the same energy, so like at 4 or 5 Tesla, so essentially this room at 4 or 5 Tesla, and still keeping their noise at at order 10 to the minus 15 or so, relative to the intensity of the magnetic field. So it's not a trivial feat. Additionally, in each one of these points, you need to resonate. So it's a very long experiment because, well, as I told you, the typical quality factor for this dark matter is 10 to the 6, okay? This means that you are dividing this frequency interval into little bits that are a millionth of the mass or the frequency. So let's say if you want to go from 1 megahertz to 2 megahertz, you have 1 million points. And at each point, you have to resonate, so recalibrate the experiment, et cetera, et cetera. So to really cover all these regions, it takes decades. But it's possible, probably, okay, with some big effort. However, well, let's, so, okay, so these are all nice ideas, but there is some sort of intrinsic difficulty if you want to go to low masses or low frequencies, which just comes from looking at the electric field that you are generating in the cavity as a function of this dark matter field. So here I'm essentially decomposing Maxwell's equations into the normal modes of the cavity. And here I'm just writing the source as given by the dark matter field and whatever magnetic field I turn on in the laboratory. So the biggest magnetic fields that we can turn on are static. So their time derivative is 0. So the only scale in the problem is the mass of dark matter. And if you look at what this means, it means that the source here for your signal decouples. So it gets smaller and smaller when the dark matter mass becomes smaller. So at some point, also these ideas lose steam. You cannot keep going forever at low frequency. Well, we proposed a small variation over the first cavity idea that can solve this problem. So now imagine that you tune a cavity. So you essentially choose the height versus the radius in such a way that there are two modes that are close to each other. So one is at omega 0, the other one is at omega 1. And then you put energy in the one at omega 0. When a dark matter field arrives, it's going to convert some energy from the one at omega 0 to the one at omega 1. So now you need just to tune the one at omega 1 to be at omega 0 plus or minus the dark matter mass. So these are several advantages. Well, the first one is that you can just use your nice 10 centimeter, 50 centimeter cavity to scan a huge range in frequencies, because you just need to scan the splitting between these two modes. So deform a little bit the cavity. You don't need to build a new cavity every time to resonate at a different frequency, which is bigger and bigger. Well, the second advantage is that now you introduced another, let's say, scale in the problem. So when you take the derivative of the magnetic field, you get this frequency omega 0 that can potentially be much bigger than the mass of dark matter. And so as you go to low frequency, you get a bigger and bigger advantage in the amount of signal that you have. And this is reflected in, well, the range that we think we can probe. So you see, we probably can probe a much, much bigger range in parameter space, with the caveats I was telling you before. So this is a very long experiment. So from here to roughly here, it's resonant. So at every point, you have to do the same that I described before. So there are millions of points from here to here. However, from here to here, it's broadband. So you can cover all this maybe in a couple of years or so. The other advantage, let's say, compared to these other ideas, is that you don't need these gigantic magnetic fields, but you're mostly relying on big quality factors of superconducting cavities. So the magnetic field here is like 0.2 Tesla, 0.1 Tesla, whatever you can support in a superconducting cavity without quenching it. And so you're trading, let's say, a huge amount of energy for a very large quality factor coming from the superconductor. Having said this, well, it's still a very long experiment, and it's a theoretical idea which has to be realized in practice, but there are 3 prototypes that are being built, and well, we're happy and optimistic, and let's see what happens in the future. But aside from this, let's say the take-home message from this story is that we have an idea on how to probe this line, let's say from here down to here. And well, the couplings that you get roughly here, so these photon-to-photon couplings, come to scales FA of order 10 to the 15 GeV, so the GAT scale, which is a particularly motivated point. It would be nice to probe another couple of orders of magnitude, then you hit 10 Planck, and then it starts becoming very hard to build models much farther down. But well, so very roughly speaking, we have an idea on how to cover the vast majority of this line, which is motivated theoretically from here to here. Above, there are many other ideas, which are typically, again, variations on this cavity paradigm. So instead of having an empty cavity, you put something inside that changes the typical resonant frequency, and that allows you to go higher in mass. So the very rough take-home message from this first part of the talk is that, well, I think that ultralight dark matter is interesting. It's at least as motivated as the candidates that we've been looking for decades. But we just started looking for it experimentally. It's hard, but not impossible. And well, we have ideas to cover most motivated parameter space, but there is still a lot to do. So if you're interested, this is not a bad time to start thinking about it. There are holes. So you see this coverage is not perfect. There are holes here, holes here. There is, of course, the question, which is much harder, but very interesting, of how to go down here. And eventually, well, if we probe all of this orange line and find nothing, well, there is a whole range down here, which is almost as motivated and much more challenging to explore. So there is a lot of fun to be had, I think, both for experimentalists and theorists. And with this, well, I can wrap up, let's say, the first part of the talk. The second one is shorter, so I don't know. Well, I still have some time. And right, so if you have questions on this part, I'm happy to take them now. If not, I can move on to gravitational waves. Yes.
Simple question. So with any bosonic dark matter, I mean, any region parameter space of ALPS, you can reconvene or solve basically the discrepancy with the dwarf galaxies dark matter densities, or
any, you said? Well, I don't think so, in the sense that
so do you have there is a limit here that you can put from dwarf galaxy, or
you mean like just so dwarf galaxies, yes, can exist anywhere here. However, so if you want to solve some small scale structure problem, either in our galaxy or you, so if your question is the prediction of this dark matter different than cold, like vanilla cold dark matter in lambda CDM, you start seeing a difference only around here. So where the masses are 10 to the minus 20, 21 eV. From here up there, it's almost identical to lambda CDM, unless you start probing scales that are of order of, so you see, so the fact is that this scale, 10 to the minus 20 eV, 10 to the minus 21 eV, is roughly the size of a dwarf galaxy. So 1 over this mass times its typical velocity is roughly a kiloparsec, let's say, okay? So if you keep going up here, you're starting modifying scales compared to lambda CDM that are really small. So there where I think it's exceedingly hard to make a prediction that you can test. So for all practical purposes, all this region here, it's identical to lambda CDM. If one day, well, some of you will be able to compute these under and over densities at, say, the planetary level, then there will be a difference. But well, yeah, no problem.
You started testing this heterodyne detection?
Yeah, so these prototypes. So this one has already taken data, the one at Slack. So it's well, it doesn't really have any, well, you see it in the plots mostly called like SRF or something like, but we haven't published a paper yet. So we have some internal results, but we've been slow at writing them down. This one at Fermilab, so there is a paper, but that just describes the concept and the cavity they're gonna use. I think now they're taking data, but there isn't a paper with data yet. And the one at CERN has the money, but no one started building the cavity yet. So that's roughly the stage. So for this last one is the, let's say, most interesting from the point of view of the experimental concept, because you see, I drew these fins here, which are one idea on how to scan the frequency splitting between the two modes, because one mode is going to have one polarization of the electric field that doesn't see the fins, so it ends, let's say, on the blue area. The other one instead is going to have the electric field that's orthogonal, so it sees the fins and it ends on this red area. And so by pulling them in and out, you change the splitting. And that's, of course, the most, let's say, the most tricky part to do experiment, and the Slack prototype is testing it, at least in a small frequency range. On the other end, it's made of copper, so it has almost no sensitivity to physics. Instead, these other two are going to be superconducting, and even if there are small prototypes with much small, well, they're still going to start like probing some new parameter space. Yeah, sorry, I saw a question.
So there was an idea long ago, putting together a superconducting ring and seeing. So these guys are oscillating, right? So does this oscillating axion field can produce, like from nothing, a current in a superconductor, for example, or you need to sort of find external field, like your? Well,
so this from nothing, I'm not sure. Let me think. So this idea here, so the green lines are similar to what you described, but they have an external field. So they have this big static external field, and then they use a superconductor as a squid detector, let's say. So it's not exactly what you're saying, but similar. To literally have it generate something from nothing, I mean, it could, in the sense that there's always electric fields inside nuclei and molecules, so it could happen in principle, but I don't see how it would happen, because here, to see anything, you need these huge background fields, you see, that are coherent. So it would happen that if the axion comes in, it interacts with, say, the nuclear electric field and generates some photons. But this is more of a like really a particle level process where you see single photons coming out. So I think it would be cool to explore it, but yeah, I mean, it's hard for me to imagine that they're going to be sensitive in these ranges where the couplings are so small. And sorry, I should maybe add one tiny thing, which is now I'm showing you these two, let's say, concepts, but mostly for lack of time. Okay, there are tens of ideas that cover this space. These two that I'm showing you are just the ones that cover the most, let's say, log territory. Okay, the other ones cover smaller regions. Yes.
Understand what happens at very low frequencies. So you said that, I mean, you have two modes at high frequencies. And
yes.
The resonance is done overlap. So you have to tune them.
Yes.
But, is there a problem? I mean, when the two modes overlap, I mean, the idea is you externally excite one, and then the axion field puts energy into the other. So what happens?
No, so indeed, that's a background that we always have and that we've included, because even when they're very separate, okay, there is like some tail of the Breit-Wigner of one going into the other. And from here downwards, you don't have the ability to control the frequency splitting finely enough to resonate anymore, which means effectively that the two modes overlap. And the way in which we separate them is in some sense purely geometrical, because if you want an axion signal, you need the electric field of one mode to be orthogonal to the electric field to the other mode. And well, in this Slack cavity, which is for now the only one that demonstrated this concept, essentially they have a pickup for, say, the signal field, I think at the bottom or at the top of the fins, where the other one is almost zero. And then they have a coupling to the one that they want to load on the other side, either at the bottom or the top of the fins. Now I forgot which one. And they have demonstrated a splitting purely coming from geometry at a parting 10 to the 3 in amplitude, so 10 to the 6 in power. And that's roughly how you distinguish them. Plus, there is the fact that the cavity is very narrow. So in this projection, I'm thinking of a superconducting cavity with a Q of order 10 to the 10, 10 to the 12, which means that even if the two modes are very close, they're not really overlapping. So you still have some separation power just purely coming from the fact that they're so narrow in frequency space. They really go on top of each other only in this region here that is flat. So there are these two handles. So there is the geometric separation, which here is all you can do. And then you start getting more sensitivity, because then you start really separating them also in frequency space. But indeed, yeah, so this is one of the hardest things to do in this experiment. But okay, one other reason why we're optimistic is this gravitational wave story that I'm going to tell you in a second, because this heterodyne idea actually comes from a much older idea for gravitational waves, which is basically the same. And here, they were able to separate the two modes at a parting 10 to the 7 instead of in 10 to the 3. But that they were helped by the geometry, because in the case of the gravitational wave, the two modes, so the one that you put energy in looks like this, with two electric fields going parallel in the two cavities. And the one that you want to read out as a signal looks like this. And so you can build a readout that sums the electric fields or subtracts them. And so there it's much easier to get a big separation. So we're still trying to engineer something as clean as this also for axions. Yeah, so were there other questions? All right, so if not, I'm gonna move very quickly on to gravitational waves. Please stop me anytime if I need to cut. So as I said, so this dark matter looks a lot like gravitational waves. It's a classical field with a tiny coupling. And well, as I just said, you're not gonna be surprised by the fact that I got this heterodyne idea from a gravitational wave experiment. In principle, you can do also the opposite. You can repurpose light dark matter experiment for gravitational waves. But if you do it, you will find always that the sensitivity is awful, especially if you're interested in looking for primordial stochastic background of gravitational waves. Okay, to me as a particle physicist, these are very interesting because they allow to probe you potentially some very high energy phenomena that we're never gonna be able to probe in the laboratory. And so, well, in the next few slides, I wanna focus on these signals. So they appear in your detector as some sort of stochastic noise at high frequency. Well, so we were playing with these axion experiments, gravitational wave experiments. We wanted to see these signals, and then we started doing some estimates. And we found that it's essentially impossible to detect them above a certain frequency. And that's what I'm going to show you now. So it's really a simple exercise that you can give to your undergrads if you want. But surprisingly, few people in this high frequency gravitational wave community have considered it so far as I know, because there are some proposals that just go out there and want to measure gravitational wave at a terahertz or at a gigahertz. And as I show you in a second, it's just like a ludicrous enterprise if you want to really detect these stochastic backgrounds. So the summary of this part of the talk, which is also the conclusion, is that, as I just said, there is a big effort to try to detect high frequency gravitational waves. There are a lot of signals that are very motivated and I'm personally very interested in. They go from phase transitions in the early universe to signals from inflation to primordial black holes. However, most of them are just hopeless. And it's not a theorem, so someone can always come up with a clever idea to enhance by 10 to the 50 what I'm going to show you. However, well, you will see how hard it is, okay? So to let's say, to some extent, prove or make more plausible my statement, I'm going to have two toy models of what's a gravitational wave detector. One is just a box with electromagnetic energy. So there is some electromagnetic field E0 and some volume. The other one looks more like LIGO and Virgo, and that actually is the one to which you can map most high-frequency gravitational wave detectors. And if you want, I will tell you also which ones you can map on it. But very roughly speaking, if you just want to know what's the best possible sensitivity of the detector, these two toy models at high frequencies do it. And the second toy model is just another box with electromagnetic energy in it, with a wall that can move and has a big mass. That's it. So this also describes a laser, by the way, which is just electromagnetic energy at one particular frequency. So it's not different than putting electromagnetic energy at in some fixed mode of a cavity. And so the first thing I want to do is to write the equations of motion for this test mass, which are just these. And okay, you see immediately, and you probably already know that if you take the mass to infinity, well, the signal, because of the equivalence principle, remains constant because the gravitational and inertial mass are the same, but noise goes to zero, okay? And that's what I'm gonna do. So I'm going to imagine that I have a wonderful detector where I can completely neglect all noise sources. So I'm just sending this mass to infinity and forgetting about it. So I'm not even asking if this is reasonable to do experimentally. Then, okay, then my detector toy model number 2 and detector toy model number 1 become effectively the same toy model. So you just have to describe the electromagnetic readout of your signal. In practice, you're just saying that you have some energy in your detector or some electric field at some frequency omega 0, the gravitational wave arrives and generates for you two sidebands, one at omega 0 plus the frequency of the wave, and one at omega 0 minus the frequency of the wave. And I'm gonna call these, let's say, signal electric fields E sub H. That's it. Then, of course, okay, if you want to describe every detector in detail, you need to model how, let's say, this movement of the mass is translated into an electromagnetic signal. And I'm going to do it via some transfer function. However, given the limited time, I'm not going to tell you what the transfer functions are. I'm just going to tell you that with this very, very simple toy model, I can reproduce the sensitivity of a variety of existing and proposed experiments. So here I have a search of LIGO for primordial stochastic background. And this is my, let's say, estimated lower bound on its sensitivity. So here, as I said, I'm making all assumptions possible that makes the sensitivity as good as it can be. And the difference that you see here just comes from the fact that I've imagined that here I have a spectrum of primordial gravitational waves, which is flat over all this frequency range, where the LIGO signal was some more realistic power loss. So the difference here comes purely from what I assumed on the signal. Then you see that also for Weber bars or for, say, big magnetic cavities, smaller magnetic cavities, the holometer, bulk acoustic wave oscillations, I always have an estimate which is slightly below the actual sensitivity, which is exactly what I want. So I want a lower bound on the sensitivity of the detector. So I'm just gonna give you 2 more slides with the details of how I get this lower bound, and then show you what this implies for high frequency gravitational waves, which is sad but also entertaining. So very broadly speaking, I can have 2 types of signals. Either one that is linear in the strain or quadratic. So my signal energy is going to be some electromagnetic energy, which is either proportional to h and the electromagnetic energy that I put in the experiment, or h squared and the electromagnetic energy that I put in the experiment. The reason why I care only about electromagnetic energy, sorry, is what I said at the beginning, that I'm imagining that I'm already sending the mass of the test mass to infinity. So I'm already doing the best I can possibly do with the mechanical energy, say, in the detector. Okay, so let's first look at quadratic signals. So if the signal is quadratic in strain, this means that there is no interference between the signal electric field and the electric field that I put in my experiment. If there was, then I would be looking at a subleading signal, because I could also look at a linear signal in strain. This, just by Fourier transforming, implies that these two do not overlap in frequency space. So these angular brackets in frequency have also an integral over frequency. So the situation is roughly like this. You have some energy in your detector without the signal, and then you generate some energy when the gravitational wave arrives that is very far away in frequency space from the one you had initially. And so you can just build the detector so that it's looking in this window in frequency space, which means that if there is no signal, there is also nothing in this window, modulo quantum fluctuations. So I'm going to put 1 photon from quantum fluctuations as my noise, nothing else. If instead the signal I'm looking at is linear in H, it means that there is an interference between my signal electric field and my background one. So they overlap in frequency space. So when I build my detector to see the signal, even when the gravitational wave is not there, I'm going to have some noise from the signal, from the electric field that I put in the experiment, which is roughly given by the square root of the number of photons. Okay, this here is written in a way that maybe it's not familiar, but it's the usual Poisson fluctuations of how many photons you have in the laser or shot noise. So as a consequence, well, I can just get what's the minimal strain I can detect by very roughly comparing my signal power and my noise power, and I get the same result in the quadratic and linear case. So I get something that scales like the electromagnetic energy in the detector times the integration time. So how long I'm going to operate the detector for. Okay, so this is very rough. In the paper, we did something more sophisticated with a test statistic, a proper statistical treatment of the signal. We also, so here I'm also imagining that you have a single beam in frequency space, which is 1 over your integration time, but you can also imagine that you have many beams, and then you're going to get a slightly different expression. But whatever you do, you're going to end up with the plots that I'm going to show you now. So if you take this minimal strain and you convert it into an energy density of a stochastic background that you can detect, well, you're going to find this result. So this is the bound from Big Bang nucleosynthesis and the CMB, so just from Hubble expansion on these primordial backgrounds. If you want to do, well, imagine now that you take 2 interferometers of the same size as LIGO, operate them for 1 year in coincidence, you do optimal filtering, but your laser has the same power as that you need to turn on everything in New York City, so roughly 1% of the US power grid. That's what you can do. So you don't do better than the cosmological bounds above not even 10 kilohertz, so a few kilohertz. These other green lines are equally crazy. So they are like resonators, electromagnetic resonators with as much energy as ITER, so 10 to the 12 joules, with quality factors of 10 to the 6, again, operating for 1 year at every point. So it takes 10 to the 6 years to scan all this line. Still, they don't go beyond the cosmological bounds at around 10 kilohertz. But you can tell me, okay, fine, you're being crazy, but this is a classical experiment. What if, okay, some god of the experimentalist comes down and is able to entangle every single photon in the LIGO laser? Well, let me show you what happens. So in the quadratic case, nothing essentially, okay? Because you had one photon of noise from quantum fluctuations, the standard quantum limit. Let's say you squeeze them to zero, okay? To squeeze them to zero, you need to prepare a quantum state with infinite photons, but let's forget it, okay? You squeeze it to zero. Well, then if you want to see a signal, you still need to see at least one photon within the full operation of the experiment. So in the end, you get roughly the same target. However, for the linear signal, instead, there is potentially a big gain to be had if you use quantum resources. So you can, in principle, go from this, let's say, standard quantum limit, which has a background that scales like the square root of the number of photons in your initial electric field, to one, which is, let's say, the best you can do consistent with first principles in quantum mechanics. So let's imagine that we did this. In practice, we are very far from being able to do it, because if you really want to go from the square root of n to 1, you have to entangle, as I was saying, every single photon in the LIGO laser. But okay, let's imagine that you can do it, or in the Virgo laser, or in any other experiment that you can imagine. But let's say that you can do it. Again, so two interferometers of the same size of LIGO or Virgo in coincidence with optimal filtering, where I've entangled every single photon in their laser for 1 year, and I kept optical losses at 10 to the minus 9, because otherwise all this work is useless, gets me to 1 megahertz. Okay, so I mean, so for maybe I should say, I don't believe that we can do any of this. Okay, so I don't think that these curves make sense. So this is to show you that even if you are as crazy as you can be, still there is no way that you do better than cosmological bounds above a megahertz. Well, then I'm showing other lines that are equally crazy. If you want, I can tell you the details, but you see they do even worse or comparable. So this is a 10 Tesla magnet in a meter cube, resonating at 10 to the 6 at every point. So it takes millions of years to, maybe billions of years to scan this line. With no noise. So you also squeezed its vacuum noise to 0, essentially, and you see, okay, that's comparable to Heisenberg interferometer, which sounds a bit like some Japanese robot from an anime. But okay, so the bottom line is this. So no matter, so these bounds that you get on the strain are very simple to get. They come from the exercise I showed you. If you take them and just dial up to 11 the energy that you can put in your experiment, the integration time, still at some point you lose steam. You cannot go at much higher frequencies than what we're currently probing with interferometers. This is sad because there are a lot of nice signals up there, but it's also a fact. So when you build a high frequency gravitational wave experiment, you should probably build it here, and definitely not here, okay, if you're interested in detecting some primordial signal. The caveat with this story is that transfer function I was showing you before, okay? If you can invent an experiment which has a transfer function which is 10 to the 100 times better than an interferometer, well, of course, you can go as far down here as you can, as you want. However, you should already keep in mind that this transfer function for an interferometer or a resonant experiment like these ones with a big quality factor is already of the order of 10 to the 12 or 10 to the 10. So it already entails a huge amount of creativity and experimental prowess to do it. It's not like we're talking about enhancing the signal by a factor of 5. Okay, so existing experiments are already enhancing the signal by a factor of 10 to the 12. And if you take them and pump in them an insane amount of energy or entangle every single photon in them, still you have an hard time going much beyond what interferometers are already doing. So to conclude the second part of the talk, I'm sorry if I went a bit over time. Well, I'm going to say the same things that I said at the beginning. So there is a big effort to detect these high-frequency gravitational waves, which personally I find very motivated, at least theoretically. But sadly, if you actually try to estimate what this will mean, well, it will mean that we're not going to see these primordial backgrounds much above LIGO and Virgo. And the reason is actually trivial. So I could have summarized these 10 slides into one, which is that, well, experiments measure strain, but signals produce energy density. And the energy density goes like roughly frequency cubed times strain squared. Of course, okay, the exact power of frequency depends on the spectrum of the signal, et cetera, but there is always a big positive power of frequency times the strain. So there is this fundamental tension when going to high frequency between what the experiment measures and what the signal predicts. Okay, so this was all. Thank you very much for staying with me also in the extra time.